the eternal darkness and void of the cosmos lie unimaginably vast distances. Light takes over for years to travel from the sun to the nearest star. Our Milky Way is an island of stars spinning across this boundless black canvas. Yet within this seemingly empty interstellar space, absolute emptiness does not exist. Here, like countless silent travelers composed of rock and ice, these interstellar objects drift between stars, journeys that may span millions or even hundreds of millions of years. They are cosmic drifters, ejected from their birth star systems, carrying secrets about the formation and evolution of other stellar worlds. One such interstellar traveler is now quietly approaching the edge of our solar system. Its story began on an ordinary night of observation here on Earth. Let us turn our gaze to the volcanic peaks of the Hawaiian Islands. Here stands one of the observation sites for the ATLAS project. ATLAS stands for Asteroid Terrestrial Minus Impact Last Alert System. The name clearly reveals its mission. It is an automated sky-minus surveying system dedicated to searching for near-Earth objects that may pose a threat to Earth. The system consists of 2 telescopes positioned far apart. They work in tandem every night, scanning the sky at an extremely high frequency in an effort to detect any moving points of light. Each ATLAS telescope is equipped with a half-meter diameter Schmidt optical system. Its field of view exceeds 5 degrees, equivalent to a sky area spanning 10 full moon diameters. This expansive field of view enables highly efficient coverage of vast celestial regions. On every clear night, both ATLAS telescopes execute pre-programmed scanning sequences. They perform multiple exposures of the same sky region, spaced approximately half an hour apart. By comparing images captured at different times, the system's software automatically identifies moving targets. These targets are typically main-belt asteroids orbiting between Mars and Jupiter, or more distant trans-Neptunian objects, along with occasional near-Earth objects posing potential hazards. The system detects tens of thousands of moving points of light each night, the vast majority of which are known objects. This complex automated pipeline filters out suspicious targets and generates preliminary reports. The entire process requires minimal human intervention, embodying the high degree of automation in modern astronomy. On that decisive night, the telescope pointed toward its scheduled celestial region as usual. The camera shutter opened and closed under precise control, capturing photons from the distant cosmos. Among the thousands of recorded light points, one stood out distinctly. Its brightness was extremely faint, reaching only magnitude 20.5. This figure may lack intuitive meaning for the average person. Let's use a simple analogy. Observing an object at magnitude 20.5 is akin to trying to see the faint glow of a candle from 1,000 kilometers away. The difficulty is evident. In the initial automated classification algorithm of the ATLAS system, this light point was labeled as an ordinary asteroid. The algorithm made this determination based on its movement speed and brightness characteristics. Numerous similar small celestial bodies exist in the vast outer reaches of the solar system. They move slowly and are dimly lit, making the initial classification seem reasonable. This inconspicuous light point was temporarily archived, submerged in a sea of observational data. Yet scientific discoveries often lurk within these easily overlooked details, awaiting a keen eye to uncover the truth concealed within. Astronomers routinely review candidate lists generated by automated systems, relying on experience and deeper analysis to identify objects of special value. When this target appeared on a Ray-minus examination list, several researchers noticed anomalies. Despite its faint brightness, its trajectory showed subtle deviations from typical outer solar system objects. It was precisely this elusive difference that prompted them to initiate follow-tracking observations. Without this extra human intervention, the story of this interstellar visitor might have ended there. It would have continued its silent journey through the solar system, unknown to humanity. It was human curiosity and the rigorous scientific spirit of verification ensured this faint speck of light was not ultimately drowned out by the cosmic noise. Thus, the object provisionally designated 18F's ROM to enter a deep observation process. Over the following nights, large telescopes were mobilized and pointed in its direction. More observational data was collected, and its trajectory became increasingly clear. Initial orbital calculations indicated it appeared to lie beyond Neptune's orbit, approximately 4.5 billion kilometers from the Sun, the cold, dark edge of the solar system. Preliminary estimates placed its diameter between 208 kilometers, placing it within the typical range of small solar system bodies. All evidence seemed to point to it being an ordinary distant asteroid, but as data from the seventh night of observations entered the calculations, orbit-fitting specialists began to detect unsettling anomalies. The object's motion could not be perfectly explained by any known solar system gravitational model. Its orbital plane formed a significant angle with the plane of planetary orbits. This angle approached 90 degrees, meaning it traversed the ecliptic plane nearly vertically. This anomaly immediately raised alarms. In planetary science, most solar system bodies move within roughly the same plane. This is dictated by the formation process of the primordial solar nebula. A body possessing such a high orbital inclination must have an extraordinary origin. Researchers began calculating more precise orbital parameters with palpable excitement when the final results appeared on the screen. The room filled with shock and disbelief. The calculations revealed this object's orbital eccentricity was as high as 1.2 in classical celestial mechanics. Orbital eccentricity is the key parameter describing a track's shape. A circular orbit has zero eccentricity. An elliptical orbit has an eccentricity between 0 and 1. A parabolic orbit has an eccentricity precisely equal to 1. Yet this object's eccentricity of 1.2 clearly exceeded the parabolic threshold. This signified it possessed an open hyperbolic orbit. Hyperbolic orbits carry profound physical significance. This indicates the object is not a permanent member of the solar system bound by the Sun's gravity. It originates from infinite space beyond our solar system. Ultimately, it will escape the Sun's gravitational pull and return to the infinite expanse of interstellar space. Our solar system is merely a temporary stopover in its long journey. It is the third confirmed visitor from another stellar system in human observational history. This discovery instantly expands our vision from the solar system to the vastness of interstellar space. Each such interstellar traveler is a living cosmic museum. They carry within them primordial information from their birthplace. This information is crucial for our understanding of planetary system formation and the distribution of matter in the universe. Behind this faint speck of light lies a distant world we may never directly reach. Its arrival provides us with a precious laboratory for studying exoplanetary systems, and it all began on that night when the telescope captured that unusual speck of light. Thus, our story officially unfolds. The initial 3 nights of observational data provided the foundational material for orbital calculations. Astronomers employed a mathematical optimization technique known as the least squares method. This approach essentially seeks an orbital curve that best fits all observed positions. Preliminary calculations assumed the object was primarily influenced by the Sun's gravity with no significant external perturbations. The results revealed an elliptical orbit that appeared plausible. Its aphelion extended far beyond Neptune's orbital range. This aligns with the characteristics of a solar system copulation known as trans-Neptune objects, given its slow apparent motion and faint brightness. The research team initially classified it as a possible centaur object in their preliminary report. Such objects typically operate in unstable orbits with relatively short dynamical lifetimes. However, as observational data from the 4th, 5th, and 6th nights were progressively acquired, the calculated orbital solution began exhibiting subtle drift. The minute this drift exceeded the permissible range of observational error, residuals from orbital fitting revealed a systematic deviation. This indicated a fundamental flaw in the initial elliptical orbit assumption. When high- quality data from the 7th night arrived from Chile's Very Large Telescope, the turning point finally emerged. The new data points fell entirely outside the orbital range predicted by the first 6 nights' data. This discrepancy was so pronounced it could no longer be explained by observational error. It strongly hinted at a more astonishing possibility. The project team's orbital dynamics specialists immediately convened an emergency meeting. Their first suspicion was whether the computational model itself contained flaws, or whether it had overlooked crucial physical factors such as the effects of solar radiation pressure. Yet for an object potentially reaching kilometer-scale dimensions, solar wind pressure would exert negligible influence. After ruling out technical errors, all attention focused on to critical orbital parameters: the orbital inclination and eccentricity. Orbital inclination quantifies the tilt of an orbital plane relative to Earth's orbital plane, the ecliptic. Most cometary and asteroidal orbits within the solar system exhibit minimal inclination, typically under 10 degrees. This stems from the angular momentum distribution of the protoplanetary disk during the solar system's formation. Yet the orbit of this temporarily designated object 18F's ARO-M2, after precise calculation, exhibits an orbital inclination as high as 70 degrees. This is an exceptionally anomalous value. It implies the object entered nearly perpendicular to the plane of the planetary family. Such a highly inclined orbit is extremely rare within the solar system. It typically indicates the object experienced a violent gravitational disturbance event, such as a close encounter with a giant planet, or that it was never a native member of the solar system. Another decisive parameter is orbital eccentricity. Eccentricity defines the shape of an orbit. That represents a perfect circle. Values from 1 to 0.99 denote varying degrees of elliptical orbits. 1 represents a parabola, while values greater than 1 denote an open hyperbola. For bodies gravitationally bound within the solar system, orbital eccentricity is strictly less than 1. Final precision calculations reveal 18F's ARO-M2's orbital eccentricity to be 1.2. This result carries exceptionally high statistical confidence. An eccentricity of 1 point to this is a watershed figure. It unequivocally declares that this celestial body's kinetic energy exceeds its potential energy within the Sun's gravitational field. It possesses sufficient velocity to completely escape the Sun's gravitational captivity. From a physics perspective, the hyperbolic orbit signifies that the celestial body's orbital velocity exceeds escape velocity. It is not orbiting the Sun but executing a 1- wave flyby. Its path resembles a raindrop skimming glass in open hyperbola. This conclusion stunned and exhilarated the entire research team. They realized they might not be observing another ordinary solar system inhabitant. Instead, it could be a messenger from interstellar space. To ensure absolute certainty, the team contacted colleagues worldwide. They requested independent observations on verification using diverse telescopes. Over the next 40-8 hours, observational data from multiple observatories in the United States, Europe, and Japan flowed continuously into the database of the International Asteroid Center. All independent orbital calculations yielded the same conclusions: a hyperbolic orbit of interstellar origin. In that moment, its identity underwent a fundamental reversal. From a potential minor body at the outer edge of the solar system, it ascended to become the third confirmed interstellar object discovered by humankind. This discovery process itself exemplifies the self-correcting nature of the scientific method. Science never relies on a single observation or calculation. It approaches truth through constant questioning, verification, and independent replication. When new evidence conflicts with old models, science chooses to revise the model rather than ignore the evidence. The confirmation of this interstellar visitor stands as a perfect illustration of this process. Now we must formally name this distant guest. The International Astronomical Union has established systematic naming conventions for this purpose. For non-periodic comets, the designation uses the letter C followed by the year of discovery and a sequential alphanumeric identifier. Due to its distinct interstellar origin, a unique identifier is incorporated into its formal designation. It has been permanently named 3I 2019 Num. The number 3 signifies it as the third interstellar object confirmed in human history. The letter R stands for interstellar, explicitly defining its identity. 2019 denotes the year of discovery, while None signifies it was the first such object discovered in the first half of July 2019. This seemingly dry designation carries profound historical significance. It marks humanity's inception of an entirely new celestial classification system, an archive dedicated to documenting these visitors from other stellar systems. Each such designation represents an outward expansion of our cognitive frontiers. After confirming its interstellar identity, the next question naturally arises: where did it come from? Orbital dynamics specialists began trajectory retrograde calculations. attempting to extend its hyperbolic path outward to trace its origin before entering the solar system. This computation is extraordinarily complex, requiring consideration of the Milky Way's overall gravitational field, along with the faint influences of stars and interstellar matter it may have encountered along the way. Preliminary origin analysis points toward a direction within the galactic disk. However, due to data uncertainties and the immense duration of its journey, pinpointing its exact stellar origin is nearly impossible. It may have drifted alone through interstellar space for millions, even tens of millions of years. Its home may be a star long extinct or transformed. This makes tracing its origin exceptionally difficult, yet adds to its mystique. Meanwhile, contemplation begins on how it embarked upon this interstellar journey. The prevailing theory suggests it was likely ejected from its natal planetary system during its early formation by the gravitational pull of a giant planet, much like how giant planet migrations in the early solar system may have hurled numerous small bodies into interstellar space. Another possibility is its origin from a close binary star system. Such environments possess more complex dynamics, readily generating high minus velocity ejecta. It's even conceivable that its parent star became a supernova during its death. The violent explosion hurled debris from its system in all directions. Regardless of the specific mechanism, its very existence provides evidence that similar material exchanges occur in other stellar systems. This interstellar visitor, 3I 2023 Nun, discovered in 2023, joins its predecessors Oumuamua in 2017 and Comet Borisov in 2019, forming a growing catalogue of interstellar objects. Oumuamua is renowned for its extreme shape and lack of a visible coma, while Comet Borisov behaved more like a typical solar system comet. Our new protagonist, however, exhibits hybrid characteristics between the two. Comparative studies of these three objects will help us understand the extent of diversity among these interstellar bodies. Do they represent universal traits of their parent systems or stand as isolated exceptions? This comparative cometary science or comparative cometary science framework marks astrophysics' journey toward maturity, from that faint speck initially flagged by automated processes as an ordinary asteroid, to its current recognition as an interstellar messenger from deep space. This reversal of identity represents not only a major scientific breakthrough, but also a philosophical revelation. It reminds us that the universe is dynamic and interconnected. Matter is not entirely isolated between stellar systems. Instead, sparse yet genuine exchanges occur. Our solar system both ejects material outward and receives it from beyond. The arrival of this interstellar visitor is like an anonymous cosmic letter dropped into our mailbox, though we cannot yet fully decipher its contents. Its very existence conveys a powerful message. We are not alone. We are materially connected to the vast Milky Way galaxy, and its story has only just begun. In the following chapters we will delve into its physical properties, unraveling its composition and the secrets of its long journey. Before exploring the unique details of this new visitor, it is essential to revisit its two predecessors. Historical context provides a crucial frame of reference. The first interstellar visitor to enter human sight appeared on October 19, 2017. That day, the PAM-STA RS survey telescope in Hawaii captured an unusual point of light. This object was later named Oumuamua, meaning messenger from afar in Hawaiian. Oumuamua's discovery was entirely accidental, detected only moments before it was about to fly out of the solar system. This left an extremely brief window for follow-up observations, yet even this limited data was sufficient to send shockwaves through the astronomical community. Oumuamua's most striking feature was its extreme light curve. By monitoring how its brightness changed over time, astronomers deduced it might be a seagull, a shaped object with a length far exceeding its width. Its estimated length minus with ratio reached 10:1, a feature never before seen in known solar system object. This peculiar shape sparked intense debate about its structural integrity and formation mechanism. Another mystery that remains unsolved to this day is its non-minus gravitational acceleration. When scientists precisely calculated its orbit, they found that pure gravitational models could not perfectly explain its trajectory. A minute yet undeniable additional acceleration exists that cannot be attributed to the Sun's gravitational pull. For ordinary comets, such non-minus gravitational acceleration typically stems from gas jets produced by the thermal sublimation of icy material. These act like miniature rocket engines, propelling the comet off its purely gravitational path. Yet, in all observations of OMUA, no signs of a coma or tail were detected. It consistently appeared as a point minus-like light source, resembling an asteroid. To explain this acceleration without a coma, scientists have proposed multiple hypotheses. One hypothesis suggests it might be composed of solid hydrogen ice. The gas emitted when hydrogen ice sublimates under heat is too transparent for our telescopes to detect directly. Another hypothesis suggests it might be an extremely porous, low-minus density object, with a structure resembling a fluffy cluster of cosmic dust. Solar pressure alone may be sufficient to drive the observed acceleration. More daring speculations exist, including Harvard's Professor of VLS-Ray's proposal that it could be a light-sail-like artificial object. Though not mainstream, this hypothesis ignites public imagination about interstellar exploration, regardless of its true nature. As a pioneer, OMUA has fundamentally transformed astronomers' perspectives through its mystery. It proves interstellar objects are not theoretical fantasies, but observable realities, opening a gateway to the study of interstellar astronomy. Even as the shockwaves from OMUA had yet to subside, a second interstellar visitor arrived as scheduled. On August 30, 2019, a mature astronomer Gennady Borisov in Crimea, using a homemade telescope, discovered a celestial body exhibiting distinct cometary characteristics. This comet was later named Comet Borisov. Unlike OMUA's peculiarity and mystery, Comet Borisov behaved like a standard visitor. It possessed a clearly visible coma and tail, and its chemical composition closely resembled that of solar system comets. As it approached the Sun, water, ice, and other volatile substances heated and sublimated, forming spectacular jets of gas and dust. Through spectral analysis, astronomers detected molecules such as cyanide and carbon monoxide, components quite common in solar system comets. Comet Borisov's ordinary appearance is precisely what makes it extraordinary. It demonstrates that the process of comet formation in other star systems are fundamentally no different from those in our own solar system. The recipe for creating icy wanderers in the cosmos appears to be universal. Studying Comet Borisov is more direct and fruitful, because it allows astronomers to apply all the established methods used to study solar system comets. They measured the size of its nucleus, with a diameter of about 0.421 km, estimated the production and size distribution of its dust particles, and even detected radio signals emitted by water molecules. All this data provides the first reliable benchmark sample for understanding the physical and chemical properties of exocomets. Now let us turn our attention back to the protagonist of our story, the third interstellar visitor, 3I 2023 Nun. Compared to its two predecessors, it exhibits an intriguing intermediate state. Unlike OMUA, it exhibits no cometary activity whatsoever, nor is it as active as Comet Borisov. It only began displaying intermittent, faint cometary outgassing after spending some time in the inner solar system. This moderate level of activity may reflect its internal volatile content, or indicate its surface is covered by a thicker layer of protective dust that resists sublimation. Its light curve also exhibits complexity, featuring both gradual brightness increases and occasional rapid outbursts, suggesting possible uneven outflow activity on its surface. By comparing these three interstellar visitors, we begin to see an emerging picture of diversity. OMUA represent a class of aged objects that have depleted their volatiles or never contained ice. Comet Borisov represents a class of primitive objects rich in icy material, while our new visitor may occupy a transitional state between the two. This diversity holds profound significance. It reveals that different stellar systems produce interstellar bodies with distinct properties, determined by their formation location, the type of host star, and the evolutionary history of their system. Each discovery of an interstellar object is like randomly retrieving a drifting bottle from the cosmic ocean. Each bottle contains a message from a different world, By collecting and comparing these messages, we will eventually piece together a comprehensive picture of planetary system formation processes within the Milky Way, from MUA's astonishing debut to Comet Borisov's predictable trajectory, and the new enigmas brought by 3i 2023 NAN. These three discoveries clearly trace an evolutionary path of scientific understanding. We have transitioned from a state of skepticism regarding the existence of interstellar objects into a new era where systematic classification and comparative studies are possible. The legacy of these predecessors not only illuminates the path of past discoveries, but also provides an indispensable compass for interpreting the behavior of new visitors today. Their legacy is deeply imprinted in our scrutiny of each new interstellar messenger. Confirming its interstellar identity is merely the first step in scientific exploration. Next, astronomers mobilize the world's most powerful observational tools to conduct a comprehensive physical diagnosis of this visitor. The primary task is to precisely measure the size of its core. Since it has exhibited faint cometary activity, this envelope of gas and dust makes direct observation of the solid nucleus exceptionally challenging. Researchers employed a combined approach of optical and infrared observations. By analyzing reflected sunlight and its own thermal radiation, they could infer the size of the dust-enveloped core. Latest estimates place its core diameter between 0.6 and 5.6 kilometers, a broad range reflecting current data uncertainties. Even at the midpoint, it far exceeds MUA's size and rivals Brace's scale. Should it ultimately confirm near the upper end of this range, it would become the largest interstellar object ever discovered by humanity. Its surface area would be sufficient to accommodate complex topography such as mountains, canyons, and cliffs. Though its surface gravity is weak, it could still influence dust settling and the fallback of ejected material. Next comes the investigation of its shape and rotation state. By analyzing the pattern of its brightness variation over time, the light curve, astronomers can infer its three-dimensional structure. A spherical object maintains nearly constant brightness, while an irregularly shaped object experiences periodic fluctuations in brightness as its cross-section area changes during rotation. Preliminary light curve analysis reveals a complex and variable pattern, suggesting no single stable rotation period. This indicates it may be in a chaotic rotational state, where its rotational axis is shifting due to non-uniform material ejections. This complex motion provides clues to its internal structure. It may not be a single, solid entity, but rather an aggregate loosely held together by multiple components, resembling a cosmic rubble pile barely bound by gravity. Studying its surface presents even greater challenges. Visible and near-infrared spectral observations aim to detect surface material composition. Early spectra revealed a faint reddish tint. This reddening is typically attributed to millions of years of cosmic ray bombardment, which creates complex organic molecules, so minus called solents and icy and rocky surfaces. These dark red organic compounds coat the surface like an ancient patina. Yet as it approaches the sun, spectral features undergo dynamic changes. These spectral data show faint absorption lines of water and carbon monoxide ice. This indicates the sun's heat is dispersing the ancient reddish coating, exposing more pristine ice beneath. This layered surface structure resembles a cosmic onion, with each layer recording a distinct epoch in its long history. Measuring its surface temperature is another critical task, using infrared observation instruments like the Spitzer Space Telescope. Scientists measured its radiation intensity at specific infrared wavelengths and compared it with solar heating models. The results show its surface temperature is lower than that of an ideal black void at the same distance. This indicates its surface is not uniformly dark material, but contains brighter regions with higher albedo. These could be exposed ice layers, or a porous insulating surface material, like fresh snowdrifts. This low thermal inertia surface property means solar heat struggles to penetrate deeply, resulting in relatively low surface temperatures. Measurements of its velocity, while relatively straightforward, carry profound implications. Precise radar ranging and Doppler shift measurements confirm a speed of 58 km per second. This velocity far exceeds typical motions of solar system edge objects. and significantly surpasses the escape velocity from its current location within the solar system. Such high speed stands as one of the strongest evidences for its interstellar origin, yet it also raises a core question: where did this momentum come from? Within its original planetary system, it likely initially travelled at a much lower velocity, much like Kuiper belt objects in our own solar system. To attain the extreme velocity observed today, it must have undergone a dramatic acceleration event. The most plausible explanation involves a close encounter with a massive celestial body. In its native system, a Jupiter-sized gas giant could have acted like a slingshot, accelerating and ejecting a smaller object. Alternatively, it may have resided in a binary star system. The complex dynamics of binary systems serve as efficient factories for producing interstellar projectiles. It is even conceivable that the supernova explosion of its parent star at death delivered the final fatal blow, violently propelling it into interstellar space. Regardless of the specific mechanism, its high velocity itself suggests its origin in a dynamically turbulent and potentially cataclysmic environment. Its journey may have begun with a cosmic minor-scale catastrophic event. To gain deeper insights into its internal structure, researchers also monitored its activity near Pirilhana. A solid monolithic core typically produces relatively stable jets when heated by the sun, while a loosely structured aggregate may exhibit more violent and intermittent eruptions. Observational data supports the latter scenario, revealing multiple sudden brightness surges. This lends credence to the hypothesis of internal voids or fragile structures. Such a porous architecture helps explain its survival under the thermal stresses of Pirilhana without fracturing, as some predictions suggested. Its internal structure functions like a cosmic cushion, absorbing and dispersing heat and stress. Polarized light observations offer another unique perspective. When light reflects off dust particles within its coma, it produces specific polarization directions. Dust particles of different compositions and shapes generate distinct polarization signals. Preliminary polarization measurements indicate its dust particles exhibit high porosity and complexity, likely containing a mixture rich in organic molecules and silicate minerals. This bears similarities to our understanding of primordial solar system comet dust composition, yet also presents differences. Synthesizing all these observational data, we begin to piece together a preliminary physical picture. It may be an irregularly shaped object several kilometers in size. Its surface is covered by an ancient, dark red organic layer weathered by cosmic rays. Beneath this lies a sealed reservoir of water ice, carbon monoxide ice, and other volatile substances. Its internal structure is likely relatively loose and porous. As a whole, it resembles a massive, dirty cosmic snowball hurled from a distant world, now reversing our solar system at astonishing speed on a 1- time journey. Though unverifiable speculations about its origin suggest based on existing physical laws, it likely formed within a young, dynamic planetary system. There, the gravitational darts of giant planets flung countless small bodies like it into the frigid interstellar void, embarking on an endless odyssey. It may predate our solar system or be younger. We cannot know for certain, but the primordial information it carries will be an invaluable treasure for understanding the diversity of planetary systems in our galaxy. Each such dissection is an indirect handshake with distant worlds. By deciphering this messenger, we glimpse the hazy contours of its home, a place forever beyond our reach, yet accessible through scientific thought. As data from Interstellar Visitor No. 3 continued to be gathered and analyzed, a series of anomalies emerged that defied explanation by existing comet models. These anomalies not only challenged astronomers' theoretical frameworks, but thrust this interstellar traveler into the eye of scientific controversy. The first anomaly to draw attention was the distance at which its activity began. According to standard thermodynamic models, a comet with water ice as its primary volatile typically exhibits significant sublimation only when within 3 to 4 astronomical units of the Sun. Yet this visitor displayed faint but unmistakable signs of a coma at over 6 astronomical units from the Sun. This premature activity suggests its surface or interior contains substances more volatile than water ice, such as carbon monoxide or carbon dioxide ice. These substances can transition directly from solid to gas at lower temperatures, as its early spectral data revealed no strong signature of these molecules. This presents the first mystery: what mechanism drives its activity at such a distant location? Next came the peculiar fluctuations in its light curve. Most comets exhibit relatively smooth and predictable brightness variations. As they approach the Sun, their overall brightness steadily increases. Yet Comet 3I-23 Nun's brightness record featured multiple abrupt flashes. Its brightness surged over to-fold within just 6 hours before plummeting back to baseline levels within half a day. Such rapid, high-amplitude brightness variations are highly unusual. They likely stem from small scale, yet extremely violent localized eruptions, such as the sudden release of high-pressure volatiles on its surface, or the instantaneous shedding of small surface fragments due to its highly fragile structure, which increases the effective area reflecting sunlight. Either scenario points to a highly unstable and homogeneous interior. The third major anomaly concerns the nature of dust particles in its coma. By analyzing the spectral and polarization properties of scattered light, researchers discovered an exceptionally high albedo in its dust particles. This implies they possess an extremely dark color, almost charcoal-like. Yet these dark dust particles efficiently reflect light at specific wavelengths. This combination of properties is uncommon among comets in our solar system. It may suggest these dust grains are rich in complex organic macromolecules or unique mineral compositions. These substances might have been gradually synthesized during its long interstellar journey through cosmic ray bombardment of its surface. These successive anomalies provide a stage for scientific imagination to flourish. Among the most striking and controversial interpretations comes from Professor Avi Loeb, from a chair of Harvard's Department of Astronomy. Professor Loeb is not a traditional astronomer. He is renowned for proposing unconventional hypotheses and challenging scientific consensus. He systematically compiled these observational anomalies and posed a thought-provoking question: have we absolutely ruled out the possibility of artificial origins? Before exhausting all natural explanations, Professor Loeb cautiously emphasizes he is not claiming to have discovered extraterrestrial civilizations, but advocates a purely science- and data-driven approach to exploring all possibilities. His argument builds upon the convergence of several observational facts. An unusually early onset of activity may indicate the presence of unnatural insulating structures within its core. Rapid light variations could stem from a highly non-spherical geometry, such as a flattened disk or elongated cylinder, generating dramatic brightness fluctuations during rotation. He even speculates that its surface dark-red material might constitute a protective layer designed to absorb radiation, or a covering engineered to maintain internal cryogenic temperatures during extended interstellar voyages. Professor Loeb's perspective immediately sparked a storm of controversy within the academic community and among the public. His supporters praised his open-mindedness and courage to challenge established authority. They argued that imagination should not be shackled when exploring the unknown. Many major breakthroughs in scientific history originated from investigating hypotheses that seemed absurd at the time. However, the scientific mainstream responded with extreme caution and widespread skepticism. Most astronomers adhere to Occam's razor principle. When faced with multiple competing hypotheses, the one with the fewest assumptions, the simplest explanation, should be favored. They pointed out that existing physics and astronomy knowledge could construct entirely plausible natural models to explain these anomalies. For instance, its premature activity could be attributed to the sublimation of carbon monoxide ice. While the spectral lines of carbon monoxide are indeed difficult to detect at low concentrations using ground-based telescopes, their rapid light variations could be understood as localized outbursts occurring when fragile cometary nuclei heat up. Similar phenomena exist in some solar system comets, albeit to a lesser degree. Their dark dust could be explained as organic material processed in a high-radiation environment. Corresponding evidence can be found in laboratory simulations and observations of outer solar system objects. They further counter that introducing the exotech hypothesis actually introduces more complex problems. Who built it? How did it traverse vast interstellar distances? What was its purpose? Each question proves more challenging than the original mystery it seeks to solve. To test Professor Loeb's hypothesis, researchers specifically employed radio telescopes, like the Allen Telescope Array, for targeted monitoring, hoping to detect potential artificial radio signals. The result was a complete failure. No unnatural electromagnetic radiation was detected. Similarly, the highest resolution images from the Hubble Space Telescope revealed its coma to be uniform and natural, showing no signs of geometric structures. Its behavior during Paril-Hanna passage also fell entirely within the predictions of cometary physics models, showing no evidence of intelligent trajectory corrections. This controversy gradually subsided in the face of scientific methodology, yet it left behind a valuable intellectual legacy, demonstrating profoundly how science balances openness with rigor. Science welcomes bold hypotheses but demands rigorous verification. Though Professor Loeffler's hypothesis was ultimately not adopted, it compelled the scientific mainstream to re-examine and interpret every observational data point with higher standards and more refined models, thereby deepening our understanding of interstellar comet physics. This debate also vividly demonstrated to the public the self-correcting mechanism of the scientific process. Science is not a rigid dogma, but a dynamic, contentious journey of exploration. Every extraordinary claim bears the burden of providing extraordinary evidence. Ultimately, a consensus gradually formed regarding 2023 Nun. It is a peculiar, yet entirely natural interstellar comet. Its peculiarity reflects the uniqueness of its birth environment and the vicissitudes of its long journey, rather than any artificial origin. It teaches us that the diversity and complexity of cosmic matter far exceed our current imagination. Across the vast Milky Way, myriad peculiar celestial bodies formed under diverse conditions exist. Our mission is to continue observing, continue discovering, and continue using the light of reason to illuminate the truth behind these cosmic enigmas. This very debate serves as a tempering of thought, making scientific conclusions more robust and reliable. Faced with this enigmatic interstellar visitor, the global astronomical community sprang into swift action. This was not merely a competition in scientific discovery but a collaborated effort of human intellect. An unprecedented global joint observation project commenced, with nearly every advanced instrument capable of pointing toward it joining the observation effort from ground-based to space-based facilities. The scale and depth of this international collaboration set a benchmark in astronomical history. Its primary objective was to resolve the core controversy surrounding it. Was it a natural celestial body or a potential artificial object? The Hubble Space Telescope played a pivotal role. Though long past its intended surface life, its superior position above Earth's atmosphere enabled it to capture high-resolution images unaffected by atmospheric disturbances. Hubble's mission was unequivocal to capture the sharpest possible images of its core region. Researchers held their breath as the data streamed back. The images revealed a classic cometary morphology, a bright nucleus uniformly enveloped by a nearly spherical hazy coma. No angular geometric features were present, no reflective solar panels, no metallic surface glints. Hubble's image ruled out the possibility of large artificial structures with high confidence. Its morphology perfectly matched that of an icy body slowly releasing gas and dust. Next came the Swift satellite, primarily a space telescope for detecting gamma-ray bursts. Its onboard ultraviolet telescope proved equally potent for comet research. The ultraviolet band is highly sensitive to water molecules and their decomposition products. Swift conducted extended ultraviolet spectral monitoring of the target. It successfully captured distinct spectral lines of hydroxyl molecules. This provides conclusive evidence of water ice decomposition under solar ultraviolet irradiation. The variation pattern of the hydroxyl signal strongly matches solar radiation models. This confirms that sublimation of water as is the primary driver of its activity. This discovery bridges the gap between non-cometary activity like that of MUA and typical cometary activity like that of Comet Borisov, indicating interstellar objects can exist in both states. Multiple orbiters stationed around Mars also joined this event. The European Space Agency's Mars Express and NASA's Mars Reconnaissance Orbiter both reoriented their high-resolution cameras toward this visitor passing near Mars. images captured from tens of millions of kilometers away, while still unable to resolve core details, provided the most precise data yet on the overall morphology of its comet dust distribution. These data reveal that its dust jets are not uniformly distributed, but concentrated in several specific active regions. This explains its irregular light variations, as different active zones face Earth during rotation, causing brightness changes. Ground-based large telescopes leveraged their large collecting areas. The Keck telescope in Hawaii and the Very Large Telescope in Chile both successfully acquired high-resolution, near-infrared spectra. Spectral analysis, like a chemist's litmus test, revealed the rich chemical composition within the coma. Beyond confirmed water molecules, spectral lines for carbon monoxide and carbon dioxide were clearly detected, along with trace amounts of methane and ammonia. The relative abundances of these substances exhibit subtle, yet critical differences compared to comets in our solar system. For instance, the ratio of carbon monoxide to water appears higher than in most solar system comets. This discrepancy may reflect a colder formation environment or a protoplanetary nebula richer in carbon monoxide precursors. One of the most compelling observations came from South Africa's Mir K80 radio telescope array, when it detected radio signals at specific frequencies emanating from this celestial body. Misconceptions circulated among the public suggesting the discovery of extraterrestrial signals. However, scientific analysis soon provided a definitive explanation. These signals precisely corresponded to the natural radiation of hydroxyl molecules at a frequency of 1.67 GHz. This is a natural amplification phenomenon known as microwave maser in comet research. When water molecules in comets are broken down by solar ultraviolet light, the resulting hydroxyl molecules enter an excited state. As they transition to lower energy levels, they emit radio waves at specific frequencies. Mir K80 detected precisely this entirely natural physical process, rather than any form of intelligence signal. China's 5-100-meter aperture spherical radio telescope, FAST, also participated in the observation, though its exceptional sensitivity failed to detect any non-natural narrowband signals. It measured the spectral line profiles of hydroxyl radio emissions with unprecedented precision. These profile data helped scientists calculate the gas temperature and expansion velocity within the comet's coma to precisely determine its orbiting position. Global radar observation systems played an irreplaceable role. The Goldstone Solar System radar and Green Bank telescope in the United States worked in tandem to transmit powerful radio waves toward the object and receive its faint echoes. Radar observations not only determined its distance and velocity with meter-level precision, but also inferred through analysis of the echo characteristics that its surface is likely relatively smooth, without large rock formations or significant depressions. All this data from diverse platforms and wavelengths was consolidated at the International Astronomical Union's data center. Research teams worldwide collaborated through open science principles, sharing data and conducting joint analyses. This global cooperation significantly accelerated the research process. Results from different teams could cross-validate and complement each other, forming a multi-nation and comprehensive understanding of this interstellar visitor. Data fusion analysis ultimately converged on a unified conclusion. 3I 2023 None is a naturally formed interstellar comet. All observed anomalous characteristics can be rationally explained within the framework of known physics. Its premature activity stems from volatile components rich in carbon monoxide. Its irregular light curve originates from the uneven distribution of active regions on its surface. Its high velocity results from the dynamical ejection of its parent system. The success of this global joint observation demonstrates the formidable power of modern astronomy. It no longer relies on isolated discoveries, but resolves cutting-edge scientific questions through the integration and collaboration of global resources. The experience and methodologies accumulated during this joint observation will lay a solid foundation for rapid responses when encountering future interstellar visitors. When the next messenger from deep space arrives, humanity will be equipped with a more sophisticated and robust observational network to welcome them and decipher the interstellar messages they carry.